Welcome to Electrical Engineering, Chapter 1, Part 2, where we'll be discussing electromotive force, current, potential difference, and resistance in a circuit. But before we can start on with that, let us first start with the concept of charge. Now, when electrons are removed from an atom, it becomes positively charged. This is because it loses negatively charged particles. Now, if excess electrons are added to the atom, it will become negatively charged. So either you remove or add. So if you're adding more electrons, your atom will become more negative, and when you are removing more atoms, it will become more positive, as I suggested in the earlier part of this video. Now, depending on that, it will determine your overall charge of your particle, whether it becomes positive or negative. It will depend upon the electrons either you remove or you add. Now, what I'm going to do at this exact moment, I'm going to draw a table where we can put a summary of what do I mean about these charges, what's the summary and what's happening between electrons and their charging relationship. For example, a proton, a neutron, and an electron, their nature of charges, and also the charges that they possessed in terms of coulombs. So let me try and draw up this table right about now. So let us say we have a particle, can be neutron and electron, so on and so forth, and the charge possessed in coulombs. As we measure charges, we measure them in coulombs, and the nature of that charge. Let's start off with a neutron. I've done a similar table like this earlier on part 1, but that table was only describing the mass of each particle included in it. For example, we showed the mass of a neutron and its nature of charge, but now I'm gonna give the charge it did possess, which is 0 coulombs, and it's of neutral nature. Now it's the proton, and it has a charge of 1.602 times 10 to the negative 19, and it has a positive nature. Now for an electron, it has the same equal charge of 1.602 times 10 to the negative 19 coulombs, but it's of negative nature. Now, what can we do with this? How can we define our charge based on this table? Now remember, I mentioned coulombs as the measurement of charge for these particles. Now the charge on one electron is 1.602 times 10 to the negative 19. So meaning that 1 coulomb of charge is defined as the charge possessed by the total number of electrons. What do I mean? So if one electron out of how many? Out of 1.602 times 10 to the negative 19 electrons, meaning it will possess about 6, if we divide that, 6.24 times 10 to the 18, oh, it's positive 18, I'm sorry, electrons. Therefore, in conclusion, 1 coulomb of charge is indeed equal to a charge on 6.24 times 10 to the 18th power electrons. Okay. Now I think we should move on to electromotive force, and we kick off our video or our chapter or our second part of chapter 1 with current and electromotive force. Well, in order to have current, you have to have electromotive force in the first place. So let us begin. So, for example, as I mentioned earlier, we've got a copper material. Let's say this is our material. Say this is a copper wire, and we just zoomed in, say this is your wire, right? This is your copper wire. And what I've done is I have zoomed in what's happening inside it. What's happening inside this copper? I just took a section of this copper wire. Now, inside, we will have atoms. Many of them. This like that, like this. I won't draw them to be very large. Well, they are not atoms, they are the nucleus. Let me draw. There's a cloud surrounding that nucleus, which is this. They're all packed into one material with that electron cloud. Now, I will draw the electrons just now. You don't have to. Let me use a brighter color for electrons. So there, I'm gonna draw them big, and they'll be yellow. Big and yellow. Reminds me of that bird from Dagalan Sesame, but hey. Okay. These are our electrons, right? They're yellow. Now, to keep up with what I've been saying, this copper wire would be indeed connected inside a circuit. Got a positive, we got a negative, right? And it has to connect, let's say, all the way here. Let's not put a switch right now. Let's just say we have a battery and we have a wire. Okay, that's the connection. That's how basically our simple circuit will be set up. This is the cell. We have a positive and a negative terminal. These highlighted here will be free electrons. Now, free electrons are always moving in random directions, right? There is no particular direction that they will be moving. The small electrical effort externally applied to a conductor makes all the free electrons to drift along the metal in the determined particular direction. So basically, this terminal will influence the direction of our electrons depending on how you've arranged your cell, either the positive on this side or the negative terminals on that side. It will influence the direction of our electrons here. But since I've set it up in this particular fashion, it means that our free electrons will probably be attracted to this positive terminal. You see, they will drift to this positive side. These are electrons and they are negatively charged, meaning they'll be attracted to a positive. I hope you can all understand that. Let me just draw arrows that will drift in that direction. Okay. But what I meant was an effort is required in order for these free electrons to move. So we need some source of force, something to give motivation to our free, because they won't move in any particular direction unless you connected it to an electromotive force, which is in our case this cell right here that has a positive and a negative terminal. So it will influence the direction of our free electrons here in one particular direction, and this would be called an electromotive force that is influencing our electrons here. Now, the direction of conventional current, it will be opposite to the direction of flow of these electrons. So this is electron flow, basically. Electron flow. That's the direction in which these electrons are flowing. But as you may all know, we will not follow that standard direction. By convention, current will flow in the opposite direction, meaning conventional current. In this module, we'll be using from positive to negative. Current will flow from the positive terminal up to the negative terminal, which is what, clockwise instead of anti-clockwise. So it will always move in an opposite direction to the electron flow. Now, when these atoms gain or lose their electrons, they may be called ions. They are called ions, not maybe, they are called ions. Either a positive or a negative ion. I think they're named the cations or something like that, cation. Yeah. Now, this is one of the most important parts here. Very, very important part. Very important point you have got to grab in the beginning, in the foundations of this course, is that when a free atom gets dragged towards the positive from an atom, it becomes a positive charge ion. So in these atoms, this electron will move to this side, leaving this atom as what? As an overall positive atom, as a positive ion, for example. Now, if it's positive, then it will drag another electron that's negative to it, meaning now it wants to become neutral. In other words, it wants to become stable, not neutral as per se. It wants to become stable. So it will try and attract another electron from another atom in order to reach this. So this will go from atom to atom. One electron leaves, another comes, another leaves, another one comes in its place. Now the process will repeat from atom to atom, as I've said, all over this conductor. So as long as it's connected to a E.M.F. Now this will create a flow from negative to positive, as I said, from negative to positive. Now this will become our electric current. From negative to positive, they'll be attracted by this positive terminal. Okay? But again, by convention, it will go the opposite, from positive to negative. That's the flow of our current by convention. Now let's go on with the relationship between current and charge. Well, mathematics is starting right at this point. We'll start with our mathematics at this point. Now, current can be measured now by many particles. Or let me say, current can be measured by how many particles are passing through the material per second. So this copper wire, if you can measure how many particles are passing through it at a certain point per second, we can determine the current, because now we've got something moving, we've got some energy, we've got something moving that's happening inside of it. Now this is expressed in terms of charge carried by electrons in the material per second. We're going to express it in charge instead of how many particles. We're not going to say this how many particles are going. No, we're going to state it as charge. Like I mentioned earlier, we've got coulombs as our measurement of charge. And we will define it as such. Flow of charge Okay. Now, flow of charge per unit time is used to quantify an electric current. Therefore, let me change my pen and we will define what is current. Now, the rate of flow of charge in an electric circuit or any other medium in which charges are subjected to an electric field. Now, the last part you will see in the later stages of our course. This final part will become very important once we're doing let me not spoil it for you. Let me just say you will see it later on as we go through this module on what the last part actually means. Now, we already established that charge or Q is measured in Coulomb. What else? Meaning that current is measured in amperes, or in other words, as I've mentioned before, coulombs per second, the rate of charge going through that material. Meaning that in mathematical terms, I is equal to Q over T. Okay? Now, in conclusion, this will mean that 1 therefore 1 ampere or rather let me just say flow means a okay, 1 ampere current means a flow of 6.24 times 10 to the power 18 electrons per second across a section taken anywhere in the circuit. Okay. Now, with that in mind, let us continue by going through our next chapter, which is electric potential and potential